Okay, hi everyone. This is a talk on attacking Ethereum dApps. But first, quick show of hands. Who here has interacted with a dApp before? Okay, good. So this talk kind of assumes you don't have any background at all with Ethereum dApps or Ethereum in general. But the point is that dApps and Ethereum and the world of blockchain is really taking a big role in people's lives today. So it's super important for the traditional security world to understand kind of the mechanisms behind blockchain security and ways you can penetration test a dApp, for example, rather than just a regular web application. So that's kind of the intent of this talk. I work at Gemini, the next generation digital asset exchange. Very exciting company. It's kind of at the forefront of cryptocurrencies and a very cool place to be on the ground floor. And we are hiring. So if anyone here is interested, feel free to come up after the talk and give me your name and resume and all that. But even more important than that, we're having a party tomorrow at the presidential suite at the Bellagio from 7 to 11. Now I can't, I was told by the recruiting people that I can't just announce it publicly like this. So what has to happen is you have to give me your name and then I have to put you on the guest list. So you can either come up to me or just tweet at me or something, send me a private message and I'll get you added. Just mention at the door that you came from this talk, from seeing this talk. I hope to see most of you there. So again, I'm a security engineer at Gemini. I do a lot of blockchain and smart contract development work. And before that, before being at Gemini, I was at Mandiant, where I was doing penetration testing, digital forensics, and incident response. So what is a dApp? dApp stands for decentralized application. Now this decentralized part's important because it gives us a few more attack vectors than the traditional application you're used to pen testing. And hopefully by the end of this talk, you'll see that it's very easy to migrate over into the penetration testing world for dApps and smart contracts. So let's talk about what a standard web application is first. You have your client over here, you have your server. Most of the time, it's just a simple GET request or a POST request that goes to the web application. A lot of times, web applications are just a front end for a database. A way to manage the data that's being returned from that database. So when you make that GET or POST to the web app, that web app might interact with another server or a series of them, but ultimately it just sends you data back, right? GET, POST, data back with some level of indirection there. So again, you're just really interacting with the web app logic, and that's kind of the point of a web app assessment is you're going against that logic. You're looking for places where access controls aren't implemented properly, vertical privilege escalation, horizontal, things like that. So that's a standard web app, but when you introduce the dApp, the decentralized part, you have a third component to it, a little kitty. But really it's a smart contract, or a series of smart contracts in Ethereum. So not only do you have the interaction with the web application, but you also have this thing called the smart contract. This is like Web3 apps that we're talking about essentially. So the workflow might look like this. You'll do the GET or POST like you normally would to the web application. But then there's a read or write to a smart contract on the blockchain. So it's not just going straight to a database and then back to you. There might be this level of indirection where the web app talks to the smart contract. And this is kind of where new attack vectors come in. After the read or write, then the data would come back to you at the end of that. Does that make sense to everyone? Okay, cool. So the point of being able to use a dApp or being able to interact with Ethereum smart contracts through a web application is that you need to have a private key involved somewhere, right? You need to own your private key and be able to use it through this web application that ultimately talks to a smart contract. So blockchains are based on public key crypto. So how do you get a private key involved, right? So traditionally, if you weren't going through a web application, you could publish a transaction onto the Ethereum blockchain by signing the raw bytes offline and sending it to a third-party node, like Infura, for example. Or you can run a node yourself, sign the transaction, broadcast it yourself. But through a web application, how do you introduce public key cryptography with a private key you own, and that goes ultimately to, where a signed message ultimately goes to the Ethereum blockchain? So one way to do that is through MetaMask. So MetaMask is a very popular in-browser extension. I think it's something like 1.5 million total downloads so far between Chrome and Firefox. And it's a wallet in your browser. So you can interact with these dApps by having your own wallet as a Chrome extension or as a Firefox extension, sign things, have them go through the dApp like that. So this is kind of what it would look like. This would be the extension. It would pop out like this when you click on it. You have a password to seal your wallet. And this is a dApp, the CryptoKitties dApp that everyone's familiar with, at least on some level. So if you wanted to buy this kitty, for example, you would authenticate to your wallet, you'd unlock the wallet, and you click OK, buy this kitty. And when you do, you get the arguments needed to buy the kitty. So MetaMask will then populate the arguments you need, the amount of ETH to pay for that kitty, the destination, which is the CryptoKitties smart contract, and all that, and you can click submit or reject. But clicking that basically prompts you in your Chrome extension, the MetaMask extension. So this is how you can have your own identity, your own private key in your browser interacting with a dApp. So this is what the smart contract on the back end would look like. This is for the CryptoKitties smart contract. You see this array of kitty objects. There's a kitty index to owner mapping. So ultimately, when you sign the transaction, when you send the ETH and you send it to the appropriate function, like we just showed a second ago, these data structures get updated on the smart contract. So that's kind of the workflow. It goes from the web application you saw. It gives you an interface, a nice clean interface to interact with the smart contract. You send the transaction through MetaMask, and then this ultimately gets updated on the blockchain. These arguments, these data structures rather. So this is just a GIF of going through the workflow. And actually, you're going to see me buy a kitty, and I actually had to buy the kitty for this demo, so now I have this kitty. So I don't even know what it's called, Good Sire. So okay, buy this kitty. You see the prompt come up. I click submit, and now I am the proud owner of Good Sire. And Good Sire is for sale, so if anyone wants Good Sire, please talk to me after the talk. Yeah. Give you a good deal on Good Sire. Now is also a good time to tell you I'm giving away ETH. So send me 0.5 ETH, and I will send you back much more. I'm not giving away ETH. Okay, but let's talk about how you can set up a dApp in a local environment so you can do this testing yourself now. So who's heard of Truffle here? Okay, John. So Truffle is a smart contract development and testing framework. It's made by Consensus, which has really been a trailblazer in this industry, making great tools for developing smart contracts, developing dApps. But if you want to create a dApp locally that you can test with Burp Suite, for example, look up Truffle, and there's a pet shop tutorial. So that tutorial tells you step by step how to make a dApp, how to make the web application front end and the smart contract behind it. And you just ultimately run this command below, but you should look into that. So when you have that local environment set up, this is Pete's Pet Shop. You'll see MetaMask. You'll need MetaMask to interact with it still. You'll see it is installed in my browser, on the top right. And what happens when MetaMask is communicating with, so MetaMask, you can give it the blockchain to which, or the provider rather, the node provider that you want to interact with ultimately. So this is a local environment, so I'm running the Ethereum blockchain on just localhost 7545. It can communicate with that. Every 10 seconds or so, MetaMask queries out. It does ETH get block by number, right? That's MetaMask's way of saying, okay, this is the blockchain I'm supposed to be interacting with. I need to know the latest block. I need to know the most recent information about the accounts in this wallet and everything else. So every 10 seconds, you'll see a request, if you were intercepting requests, to wherever that provider is and trying to see what the most recent block is to get the most recent information. That's how MetaMask works on any blockchain you provide it, essentially, any Ethereum blockchain. So again, this is what the pet shop looks like, and this is the JavaScript that handles the adoption function. So I told you again, there was like a web application portion and then the smart contract portion, right? So if you were to click, for example, adopt Frida, this first dog right here, what you'd be calling is handle adopt. And what handle adopt does, as you can see below, does app contracts adoption deploy, then basically call the adopt function on that contract artifact. So it knows the contract because it was developed in Truffle. It's got a really nice interface, and it just calls the smart contract function adopt ultimately. So this is kind of the bridge between the JavaScript to the smart contract. And this is actually the contract behind it. So this is the smart contract. So when handle adopt is called, we saw it called the adopt function. That's the function that's actually being called. This is a smart contract. It accepts a pet ID. Frida was pet 0. So it would check that the pet ID is within range. There's only 16 pets. And then it would update the data structure to reflect that the adopter of Frida is the person sending this message. So that would be us when we send that transaction. So that's the entire workflow. So before I actually adopt Frida, this is the adopters array right here. You'll see that every adopter is just the 0 address because no one's actually adopted anything yet. But as soon as I click adopt, I submit the transaction. I notice I don't need to pay any ETH for this because it was free. The contract didn't say require the value being sent to be above this certain amount. It's free. You just click it and you adopt Frida. You click submit. And then you'll see if you checked that data structure again, that array, the first index now corresponds to the address from which we sent that transaction. So that data structure was updated to reflect that we are the owner of Frida. So what does that transaction actually look like if you took it if you looked at it in Burp? So I just showed you MetaMask coming up and you clicking submit. If you intercepted that transaction, you would see the from address right there, right? The to address is the smart contract address, the value and data, and I'll get into this more, but it's very simple. There's only 4 or 5 fields that you need to worry about. So you can see from, to, value, data, gas price. So from is my Ethereum address, the one that's being populated in the array. To is a smart contract address, the adoption contract that has the pet array. Value was 0 again because we didn't charge this contract didn't charge anything for the pets. And data was this number, this hex value 85, etc. Right? So let's break that down a little bit. Why was this the data we sent to that smart contract? It's because we called the function adopt, right? The first 4 bytes of data in the data field are the function identifier. So it's the hash of the function name and the kind of arguments that it accepts. And you can take the first 4 bytes of that hash. That is how you tell the smart contract what function you want to interact with. So that's what's taking place. The first 4 bytes of the data parameter that we provided is the function identifier of the adopt function. So once the smart contract gets that, it says, okay, these are the 4 bytes. Yep, I know that one. That's the adopt function. I'm going to send this over to the adopt function, and then it takes the rest of that data field, and it populates, and it does whatever else it needs to. The argument it accepted, again, was pet ID, and we adopted Frida, which was the 0th pet. So you'll notice that after the function identifier, it's just zeros, right? That means we're calling adopt because we have these first 4 bytes here. We strip that away, and the rest is just 0. Okay, that means you're adopting 0. You're adopting Frida. Does that make sense? Cool. So this is a really bad slide in hindsight because you can't see my mouse, but things like cross-site scripting become a lot more dangerous with dApps because what you can do is you can manipulate MetaMask ultimately to send a transaction to somewhere you wouldn't expect. And it's not immediately obvious where you're sending the transaction to with MetaMask implemented the way it is currently. So what's happening here is I'm actually hovering my mouse over that adopt button there, but I'm not actually clicking anything. And when I hover my mouse, it prompts MetaMask to pop up and say, oh, please send some Ether here, right? So if a malicious person gets JavaScript onto a dApp, what will happen is that they can get your MetaMask to pop up with a transaction. And you might think, well, I was expecting MetaMask to come up because I wanted to make a transaction on the site. But in reality, the destination address is to one an attacker owns. So it's a little bit trickier because you're trusting this extension. And the extension can seem legitimate because it's kind of outside the realm of the site, but in reality, it's malicious JavaScript that's making it come up. There was actually an instance of this in the wild that John showed me. John, do you want to stand up? Say hi. Yeah. This is John. Basically, EtherDelta, a decentralized exchange, had cross-site scripting vulnerability where EtherDelta allows you to trade tokens between two different tokens, essentially. And these tokens, when they're listed on the site, their fields populate on the site. So things like their name, their symbol, etc. So there was an attacker who made a smart contract, published it, and in their name field of their ERC20 token, they made it some malicious JavaScript. So when EtherDelta pulled basically the ERC20, basically every part of the ERC20 protocol from the contract, they loaded in this malicious JavaScript from a smart contract onto their page. And what that JavaScript did ultimately was it sent whoever's private key they uploaded to the site, it sent all their Ether to another wallet. So again, it was in the name field, there was some JavaScript there, and it was loaded into the site, and that was an example of how cross-site scripting is really dangerous when you're dealing with private keys and MetaMask, for example. So again, there's the web application logic, and then there's also this third part, the smart contract. And the important part about the smart contract is that it's public. So it's publicly accessible. There's no rule that says you have to interact with the smart contract through the web application. You can go directly to the smart contract, which introduces a whole set of other vulnerabilities. The web application might have a really well-defined way in which you can interact with that smart contract, but there might be a glaring vulnerability in that smart contract that you'd only notice if you went to the bytecode directly. So there's kind of another attack vector we're going to discuss. So smart contracts kind of serve as another data store. They're publicly accessible, and it's like everyone wrote their own version of that software to store that data, because no two smart contracts are really the same, right? You have a bunch of people making smart contracts, storing Ether in there, storing valuable customer data, and they can make it really, they're making it themselves. So it's not like there's one single instance of software people are using to store this data that's been tried and true. Every single smart contract is a little different. So there's a lot of vulnerabilities with that, as you've seen. So you kind of have this two-pronged approach. You can attack the dApp through the web application, but you can also attack it directly by going to the smart contracts as well. So beyond that, there's kind of a third prong, and I'm going to talk about that in a second. It's going through the web application to get to the smart contract in a different way. There's this concept of modifiers in smart contracts where only certain Ethereum addresses can issue the transaction. You're denied if you don't have that appropriate key, right? So only owner is an example of this. Only the owner of the contract can update this field in the smart contract, for example. A lot of these dApps rely on a special key in the web application to issue privileged rights to the smart contract based on the client's data. So I make a GET or POST request, and the web application will say, okay, I'm going to use my privileged key to write this to the privileged spot in the smart contract. So it's not just what you can do directly to the smart contract, but can you also get the web application to make a privilege right on your behalf? Can you trick it into thinking you are the owner by fuzzing the access controls of that web app? So it's kind of a three-pronged approach. What can you get the web app to return to you? Just regular web application penetration test. What vulnerability can you find by accessing the smart contract directly? And then can you get the web app to interact with the smart contract in a way it didn't expect? So as an owner, as a privileged key, essentially. So this is an example of kind of how you would sign something in CryptoKitties. This is how you would prove your ownership of a certain address, right? You would sign the message. They'd give you a message to sign, and you'd sign it, and they'd see, okay, this signature matches the Ethereum address that we're seeing from you. So in a dApp pen test, you'd want to verify that signature validation is actually being done correctly. if you could just pop out the Ethereum address that you're providing it and replace it with another one, basically say, hey, I'm not this Ethereum address, I'm this one, and you provide a signature that doesn't actually match up to that Ethereum address, you want to make sure that the web application is validating that they're saying, okay, that doesn't actually match up, we're not going to allow you to sign in. I've actually done this before where I've been able to impersonate someone else or create a denial of service for that person if they ever wanted to sign up, because I said, I intercepted the request, which I'll show you in a second, and I replaced my Ethereum address with theirs. So this is an example. So if you were to sign up, for example, you would provide an Ethereum address that you're saying I want to sign up as, and you'd provide a signature of a phrase that you would both know, like CryptoKitties in this case. What the dApp should be doing is validating that that address matches with that signature. So if you were to swap that address out with a different address, would the dApp reject you, ultimately? I've found dApps where that is the case, where that's not the case too. So CryptoKitties does that properly, so that was good to see. But when you're already authenticated, so that's how you sign in, right? You can use a private key. When you're already authenticated, you can do things like go to settings here, and you can change some variables about who you are, right? And this is kind of that duality of web applications. Not everything you change about your account or your profile requires a signature. So at some point, it becomes a regular web application, right? If you have a cookie, you can change things about yourself sometimes without requiring a password. For a dApp, it's like if you have a cookie, or if it doesn't require a signature, then you can do things without requiring a signature again. So stealing someone's cookie might allow you to do things in that dApp without actually having their private key again. So if I were to change my email or my nickname, for example, like here, you'll see it doesn't require a signature anywhere. So this is nothing. I mean, changing my nickname to Meow is not going to cause big problems for me if an attacker did that. But it's an example of where this duality exists. Not everything in a dApp relies on public key cryptography. Some of it is just a regular web application. So there's that duality there. So I'll give an example of another one that's another dApp that's designed with security in mind, and I'll talk about why these best practices are kind of implemented there, so you can understand the attack vectors that they're defending against. So Bloom is a really big app. It's a big dApp, and it's a good example of this. If you guys want to check it out, it's at bloom.co. So this is kind of the sign-up process. You would enter your name, your phone number, and email address. And then it will tell you what you're doing, right? So you're signing your email, or you're signing the message rather, to prove ownership of the key, kind of like we saw with CryptoKitties a second ago. So nothing new there. So the validation takes place against the signature and the Ethereum address you provide. But when you sign in, you're providing not only the signature, but what you're signing includes the date and your email address, right? So does anyone know why you would be signing the date and your email address when you want to sign into the dApp? What does the date have to do with a signature? Right, exactly. Yeah. So this prevents replay attacks. I'm going to get into that in a second. So this is what, if you were to intercept that request, you'd see the email address, the signature, and the date. They would validate that the date is within a certain range. First of all, it's signed properly. The date is the same one that the server has. And that date is within a certain amount of time. So if an attacker intercepted the signature of the sign-in, then they couldn't actually just replay it another time. They couldn't replay it in a year or a week or something like that, because it wouldn't be May 2018 anymore. So email address checks the wallet address tied to that email address is in their servers, right? It checks that you're saying I'm signing in as this person. Wait a second, let's make sure that key matches that person. And the date is to prevent replay attacks. So any dApp should have a signature of the email of the date in their sign up, and their sign in rather. Similarly, inviting people. This GIF might be broken. All right, but anyway, similar concept. When you invite someone to Bloom, you have to sign that person's email address. So you can validate, okay, I actually want to sign this person, invite this person and not this other person. Now let's talk about that other prong that I talked about, attacking the smart contracts directly. Smart contracts have a whole host of popular vulnerabilities associated with them. There's a really good site called dApps.co. It's like OWASP, but for Ethereum. And it talks about kind of the top 10 for Ethereum. I'm not sure how those were chosen exactly, but they're very good examples. Reentrancy attacks, overflow and underflow, denial of service. These are all good examples you'll find there. I'll give an example of an overflow. This was a recent, I think 3 months ago, 4 months ago. It's called the batch overflow vulnerability. Basically, these people implemented a token, and they wanted to make transferring tokens cost less gas by batching the transaction into one transaction rather than having individual transactions for every single transaction, right? For transfer, rather. So what they did was they implemented this batch transfer function. So you call it once, you have an array of all the people you want to receive the token, and you provide the value. Unfortunately, they didn't check for an overflow. So there's an overflow vulnerability here in which the attacker was able to basically forge the fact that they got to pretend that they had millions of dollars of tokens, essentially. And that das.co site goes into this kind of step-by-step. There's another one. So permissions, we talked about that earlier. This init wallet function, this is in the parity, one of the parity issues. This didn't have any modifiers associated with it, right? This sets kind of the owner of the wallet, and it sets who the owners are. So it wasn't in a constructor, so it's not like it was only called once. It was in a library. So anyone could call this at any point. And because anyone could call this at any point, you definitely need a modifier associated with it so you could restrict who is able to call it. So if you're going to update the ownership of the contract, you need to make sure the initial owner was the one sending that transaction in the first place. They didn't do that. So someone set themselves as the owner and blew the entire thing up. These are real world problems. I mean, these are the kind of vulnerabilities we're dealing with right now. Very simple, very straightforward. So it'll be good to have all your eyes on it after this talk, hopefully. Symbolic execution is kind of a really powerful tool to use towards auditing smart contracts. I'm going to go over a brief example of what it is and some tools out there that employ it. So instead of concrete execution where variables are given concrete values like 4 or 5 or 6, symbolic execution allows you to parse through a program and provide a symbolic value. So it's not tied to one value, but basically a range of values that are possible. So when you're going through the program, you fork at every conditional. The symbolic execution engine will essentially fork and traverse every path. And at the end of that path, when it gets to the end state, it'll tell you the conditions necessary to get to that end state. So ultimately, you can find out a way in which a smart contract could overflow by following the logic of what conditions are necessary to get there. So here's an example. This is from Mark Mossberg at Trail of Bits. They're really great people at auditing contracts, and they've done a lot of great development work. If you had a concrete value here, like var was 45, right? You'd skip the first part of the conditional, and you jump to the else. But in a symbolic, if it was assigned a symbolic value, rather, when you get to the if var equals 42, the symbolic engine would go through there. But it would also fork, and it would go down the else as well. And it would just keep in mind the values, or the conditions rather, that it needed to meet to get down that path. So when it gets to the end, it would say, okay, I had to meet this condition, this condition, this condition. Let's see if these 3 conditions are ever possible. And if values exist that meet all those conditions, then you can get to that end state ultimately. This is another slide from Mark from Trail of Bits. This is an example of how that end state calculation gets done. So when these are all assigned, when you have A, B, and C assigned symbolic values, you can go down every path here in this tree, and you'll get the end states and the conditions necessary to get to that end state. So what we're checking here is to see if that assertion ever fails, right? Assert x plus y plus not z, or z does not equal 3. There is a path in which that assertion fails, and it's when not A and B is less than 5, those are Greek letters, but when that takes place, when those conditions are met. So that's how the symbolic execution engine works. It'll tell you, okay, I got to this assert failing if and only if these criteria are met. And then what's called a constraint engine, a constraint solver, will then tell you if those constraints are solvable, essentially, if that's a valid situation, if that can happen. And the thing about symbolic execution, it's powerful against smart contracts in particular, less so for things like sandboxes. So in sandboxes, for example, it would be really valuable to be able to traverse every single path of a binary But the issue is when you're dealing with really large binaries that are importing DLLs with thousands of lines of code, it's difficult. We'd run out of computing resources. It's impossible. A lot of these malware samples send you on a wild goose chase. So smart contracts are limited in size because of gas considerations. It costs money, real money, to publish a smart contract. It costs a lot of money to issue transactions to that smart contract. So it's more powerful against smart contracts. So Manticore is a good example. I mentioned that. It's by the people at Trail of Bits. It's a symbolic execution tool, and it will traverse these paths like I mentioned. And let me see if I can get this to play. That's an error. Okay, so here's an example of it. So you have this burnable token right here. And that's the source code for it, right? There's intentionally some bugs in it. And they run Manticore against that contract, and it's going through all these end states, and it's finding the conditions necessary for that. So soon it's going to find an underflow vulnerability, and it'll essentially, see here it is, integer underflow at sub instruction. It'll remember that end state, and it'll tell you the arguments needed that satisfied that condition. An example of those arguments that satisfied that condition. Another thing for another approach, rather than doing symbolic execution, is just going through the binary yourself, right? So you can actually use Ethersplay, for example, another tool by Trail of Bits, to get the bytecode of a smart contract at an address and disassemble it and go through it. And it's very easy to do. There aren't that many instructions in the EVM. So I recommend doing it. I actually wrote a blog post about this too, which is pretty easy to follow along. And another really popular symbolic execution engine, if you are interested, is Mithril by Consensus. So similar concept to Manticore. Both have really good documentation. And I mentioned that reversing post, so I'll put it here for anyone who wants to check it out. But that's it. Thank you very much. If you're interested in coming to the party, like I mentioned, just feel free to reach out to me. And if you have a resume or anything like that, come up afterwards. So I'll take any questions. Thank you.